Ladies and gentlemen, I'd like to thank you for giving me the opportunity to present at the 2021 user meeting, and I would like to say hello to all Mechanical Finder users. My name is Luboš Řehounek, and I would like to present my research, which aims at differentiating stress distributions at the area around implants for transgingival and subgingival dental implants. The main goal of this research is to assess the stress distribution at the peri-implant area of these two implants you can see on the images. The one on the left is a homogeneous implant, and the one on the right is the same geometry, but instead of homogeneous ribs, it has a porous structure embedded into the body of the implant. The idea is that homogeneous implants are far too stiff compared to bone, and the introduction of porosity lowers the global Young's modulus of the implant and allows more load to be transferred from the implant into the surrounding bone, thus preserving its mechanical properties and allowing some mechanical stimuli. On these two figures, we can see the main differences between the homogeneous and the porous implants. The homogeneous implant on the left has a modulus of about 120 gigapascals if it's made from titanium, or its alloys like Ti6Al4V, and the implant on the right has a modulus that is about 1 or even 2 orders of magnitude lower, which suits the material properties of bone much better, as bone has a modulus of about 25 gigapascals at the highest, and usually it is even much lower. Another great benefit of the structure is that porosity also allows for bone ingrowth, so the bone trabeculae can grow inside the body of the implant and create an interlocking mechanism that prevents primary loss of stability and also provides a larger surface area for better osseointegration. On these three images, we can see some very basic comparison between the homogeneous titanium implant stem and the 3D printed porous stem in the middle. The image on the right shows a detail of the apical area with a gyroid structure. The gyroid structure is a triply periodic minimal surface, and it can either have a variable or constant porosity. The variant showed here has a constant porosity, and what is greatly beneficial is the fact that the sheet character, the wall character of the structure, allows the load to be transferred more evenly and prevents local damage, and also deposition of debris, delamination, and breaking and storage of damaged components in the body of the patient. While conventional homogeneous implants enjoy a very high rate of success, I believe there is still some room for improvement, and increasing the porosity and thus decreasing the overall stiffness of the implant can in turn eliminate or greatly decrease stress shielding, which is a very negative effect, and the aseptic loss of stability is still one of the main causes of implant failure. I believe that porous structures can help with that, as they create an interlocking mechanism, and the bone trabeculae can also grow inside of the body of the implant to prevent the primary loss of stability without infection. So in Mechanical Finder, I have imported the DICOM data of an anonymized human mandible model, and I have created a 3D model of the mandible with one tooth extracted, as can be seen on the figure on the left. Then I have created the user-specified material model from the KAYAK material model that is located in Mechanical Finder, so that each FEM element has its own Young's modulus based on the bone density. And the region of interest operations led to the creation of the full human mandible model. After that, I have extracted a single slice around the area where the tooth has been extracted, and I have used this slice in order to compare the two different variants of the dental implants. On this slide, we can see the two variants of the same implant in detail, and in order to simulate the conditions in the bone and compare the stress distributions around these two implants, I have decided to perform two simulations. and I have used the same bone segment, the same geometry, and the same material for both implants. The implants were fully embedded inside the human mandible model. The simulation was fully inhomogeneous, and for evaluation I have decided to use minimum principal stress in the bone, so predominantly the compressive stress. My assumption going into this analysis was that the porous implant, so the implant on the right, will induce greater stress in bone as it is far less stiff than the homogeneous variant and will allow for better preservation of the mechanical properties in the long term. On this slide we can see the process of creation of the porous structure. On the left figure we can see the basic unit cell of the gyroid structure. In the middle we can see a micrograph of an actually metal 3D printed gyroid structure, and on the right we can see the model that has been used in the simulation. On the second row you can also see the single gyroid equation which has been used in order to generate this geometry. This figure shows the bone segment that has been used for both analyses, and the mandible, which has been sliced up like this, has been fixed on the lower portion of the model, and on the top surface I have applied a masticatory force of 150 newtons in 20 substeps. So these are the results of the first simulation run. For some clarity I have decided to remove the implant from the bone, so the area of the bone is exposed and we can clearly see the minimum principal stresses which occur in the bone. Both implants have been placed in the same area, so the comparison is readily available, and the homogeneous variant, which is shown on this picture, induced a stress with a peak of about 7 megapascals. The compressive stresses mainly concentrate on the lower part, on the apical part of the implant, which was expected. Now please note this value of 7 megapascals when we move into the second run of the analysis. On this picture we can see the results of the second simulation run with the porous variant of the implant. As we can see, the distribution of the stress is still the same. The stresses mainly concentrate on the lower portion of the implant at the apical area, and the distribution of the stress is pretty comparable with the first variant, but as we have seen, the first variant induced a stress of only about 7 megapascals, while the porous variant had a peak compressive stress of about 13.4 megapascals. So I was very happy to see this result, because Mechanical Finder has confirmed my expectation that the porous implant will induce greater stresses. As we can see, the stress is about twice as big. Now, this is mainly due to the fact that the porous implant has lower values of mechanical properties and lower stiffness, so the bone is ready to have more load transferred into it, and therefore the stress is much higher. So all in all, my simulations have verified my assumption that the porous implant variant would transfer more load into the bone, which I consider to be beneficial, as it decreases stress shielding and also increases the longevity of the bone at the peri-implant area. The magnitude of the pores is also a major factor, as it influences mechanical behavior and also osseointegration. Osteons, the bone trabeculae, do not really like pores which are too small or too large. The literature indicates that the optimal value of the pore size is somewhere between 300 and 900 or 1000 micrometers. Now, I believe that porous implants can provide better mechanical stability, but compared to their homogeneous counterparts, they still have some issues and shortcomings, like manufacturing speed, as they are mostly 3D printed, so their manufacture takes a lot of time, a lot of resources, and is also very demanding in terms of quality, while homogeneous implants can be readily machined and their geometry is much more simple. The figures on the bottom show the evolution of the implant and how we can apply porous layers, porous surfaces, or integrate the porous structures inside the bodies of the implants, and perhaps even create implants which have a combination of homogeneous parts, porous parts, and also some stabilizing ribs. I'd like to wish all the users of Mechanical Finder good fortune, good health, and I thank you all for your attention.